8.3 Simple recurrence relations. After we solve the problem, so that means we have some idea to, do the recursion, do the arrangement, write the code. Then we need to do analysis. How many operations we need to do to solve this problem, right? Yeah, this part, 8.3, let's do the analysis part. Yeah. To do the efficiency analysis for the Tower of Hanoi problem, let's do the basic things first. Count the number of basic operations. First, we need to know what is the basic operation for this problem. Yeah. It's easy because you just move disks from one peg to another peg. That's the basic operation. Right. Move a disk from one peg to another. Okay? Yeah. Next, we need to count the number of peg moves, disk moves, to solve the whole problem. That number, that expression, we want to find. Yeah. All right. So to find the answer, we need to define a count function, C of n. Count the number of moves. That count function. Yeah. C of n. And we can easily get the recurrence relation based on the moving details we made in the previous video, right? Yeah. So we can easily get the recurrence relation. C of n, the number of moves we need to solve size n problem, we need to split into three parts. The first part, we need to solve a problem with smaller size. We spend this many moves, C of n minus 1, the first time. Okay? Yeah, the first time. After that, we need to move the bottom disk from one peg to another one. So that is this plus 1 move. After that, we need to move the higher n minus 1 disks to destination peg. So we solve n-1 problem, size n-1 problem another time. So we spend another C of n-1. Yeah. So the whole relation is like this. Yeah. Next, we need to specify the base case. Yeah. When n equals 1, that's our starting point. So we know one disk move. Yeah. That's simple. Yeah. Finally, we need to solve the recurrence relation. We need to use some math operations, some math manipulations. Yeah. To do that, how do you do the math manipulations? We need to transform the formula. That is the key part, the most important step. All right, so let's solve the recurrence relation. The main question we need to answer, how to transform the formula. How to transform the formula. That's the hardest part. If you can do it, then you almost solve it. Yeah. So let's take a look. How do we do it? Idea we used here, explore the similarity in structure. Structure. The formula has some special structure. You need to explore that. Mainly, you want to focus on the similarities in the structure. Similarity. So what's that? I need to show you. So this is our current formula. We need to explore. We need to try to, understand. All right. Here, Try to observe. We know observation is critical in problem solving. Try to get some properties from your observation. From our observation, we notice the right-hand side of the equation, there is a +1 term. But for the left-hand side, we don't have that +1 term. That means the two sides, from the structure point of view, not quite similar. Not quite similar. The structure-wise, they are different. Now, here, our idea is we try to make the structure look similar, both sides of the equation. If the structures are similar at both sides, then we can do some manipulation to take advantage of that similarity of the structures. That's the idea. All right, how to make it similar? We just add 1 both sides. Then both sides, we will get that plus something term, right? Plus something term. So we just add 1 both sides, okay? To make the equations still balanced as before, this term becomes 2. Okay? 2, okay? So +1, +2 looks different, but here there are coefficient 2 here. Can we factor that 2 common factor out? So we get this factorization, simple factorization. After that, then you compare again, you can see now we get a similar structure. C of n plus 1, C of n minus 1 plus 1. Can we treat this whole block as one particular structure block? Yeah, we can treat that. That's one specific structure object. Yeah. Object. Yeah. All right. To see that clearly, we like to introduce a new notation d of n to represent that whole structure thing, C of n plus 1. So C of n minus 1 plus 1, that is the d of n minus 1. Okay? So we do substitution, new notation. Why it is important to use the new notation? Because after we use that new notation, we get this new equation. Look at this. Is it much easier to solve than before? Before we do that substitution, the equation is like this. After we do that substitution, this +1 term is gone. Okay? And we get a new equation that is simpler. Yeah. But we need to fix the base condition, d of 1 equals 2. Yeah, because we C of 1 plus 1, so 2. All right, now let's solve this new recurrence equation. Okay, yeah. All right. When we solve, let's do another step, right? Yeah. D of n minus 1 equals 2 times d of n minus 2. Yeah. Following the pattern, so we plug in, yeah. We replace n by n minus 1, so we get this new equation. But this d of n minus 1 can be used to replace this d of n minus 1. So you can see we will write 2 squared times d of n minus 2. Okay, yeah, we get that. Can we do another time? D of n minus 2, can we use d of n minus 3 to represent it? Another time, again and again, finally, we can reach the base case. Can we do that? Finally, we will reach the base case. But for this step, many of you, I feel, may get lost. How can you keep track of all the intermediate steps? It's not that easy. Keep track of the intermediate step. It's not easy. Okay? Now here, let me give you a commonly used way to keep track of all the intermediate steps. This method, we used it before. Remember in the string matching problem, how do we figure out the location of the last substring, M string, last one? We use the invariant idea, right? Remember that? So if you still remember that video, string matching problem. Yeah. We need to figure out the location of the last M string. How to do that? We use a special method, invariant idea. Here we use that again, invariant idea. So how do we use the invariant idea? All right, so let me describe it. How do we use it? We need to find some invariant. Then we will use it so we can keep track of all the intermediate steps. All right, let's look at this expression. Okay, we try to get invariant. This 2, we represent 2 to the first power. The exponent is 1, okay? So you take that exponent number, then you plus this problem size number, the current problem size, 1 plus n minus 1 equals n. Okay? So we treat that n as the invariant. It never changes. During the intermediate steps, it never changes. All right, let's verify it another time. Here, exponent number is 2. The current problem size number, n minus 2. These numbers adding together also equals n. Okay, equals n, the invariant number. See, n. Okay. Now you do this for all the intermediate steps. Every time you move one step forward, you increase the exponent number by 1, but you reduce the size, current size number by 1. 1 higher, 1 lower, adding together cancel out, same n number. Okay? You do this all the way to the last step. Okay? So what is the last step? Last step, because you want to get the size number equals 1, the base case, then the exponent number must be n minus 1, because these two numbers adding together should be n. That's the way we use the invariant idea to keep track of all the intermediate steps. Okay? Yeah. Hope you learn this technique so you can master this technique. Then you can solve many problems. All right. At the end, to summarize the final result, we want to see, because this number is 2, right? 2 times 2 to the n minus 1 power, so you get 2 to the nth power. Okay? Yeah. D of n equals 2 to the n. Yeah. Then we need to go back to C of n, right? C of n, 2 to the n minus 1. All right, so that is the final answer. This number of moves we need to make to solve a problem of size n. Okay? And we can verify for problem size 3 because we did that explicitly. We use 7 steps, right? 7 moves. So when n equals 3, 2 cubed minus 1 equals 7. So see, the verification for our known answer is correct. Yeah, so finally, we know this is the final answer. So we stop this part 8.3.